Hi everyone, and thank you so much for coming to my talk, and thank you, Sadie, for having invited me. It really means a lot. So the presentation today is going to be on a project that we've been working on throughout my first year of PhD, and it is joint work with my supervisor, Focus here, and our collaborator, Dr. Dan from Teesside University. Right. So the project is about optimizing the cost relative to the exam. So next slide there. Of hybrid institutional incentives with the aim of promoting cooperation in finite populations. Please don't click out of the Zoom or don't be put off by the very fancy sounding title. I will explain what this is from the get-go before we actually go to the next slide. So we've got a finite population, say of n individuals, and we've got an external decision maker in the United Nations or NATO. The decision maker has the money to intervene in our population of individuals via reward and punishment, with the aim of incentivizing the players to cooperate. That's basically it. I'm going to explain a bit more in the following slides, but I wanted everyone to be on the same page before we started. Right, so the talk is going to go as follows. I'm going to give a motivated example, and I'm actually going to ask a question, so please answer it, so I don't have to answer my own question. Then I'm going to move on to the introduction, where I will present the model, as well as cooperation mathematics. Then I will be moving on to the fun part, the math results. And then I will conclude the summary and some further research parts. Right, I'm sure most of you have heard about the present dilemma, but please indulge me as I'm walking through it again. We've got three thieves, they get arrested and they are questioning by the police. They are questioned separately. That's a very important thing. They can't communicate, so they don't know what the other player is doing. And they've got the following options. They can both cooperate and go to prison for 3 years. One of them, they can the other one can cooperate, the person that's cooperated. And when I say cooperate, I mean cooperate with the police. The person that's cooperated with the police is freely, while the other person goes to jail for 5 years. And there's also the option of both defecting, in which case they both go to prison for 1 year each. And to be fair, I always ask this question, if I'm kind of running a survey on this thing, but what would you do actually if you were put in that situation? What would you, which option would you choose? I mean, obviously, it depends on whether you're on hybrid time or hybrid. Really curious. That's a Nash equilibrium, yes. That's actually the mathematical solution. The Nash equilibrium is defection, i.e. cooperating between, well, the thieves cooperating together, as opposed to them cooperating with the police. And to be fair, take nothing else from this talk today. In game theory, which is basically a theory of conflict, so the theory of life, so I guess it can be applied to everything. Unless one has that one strategy that's always going to make one a winner, one's always better to cooperate, better off cooperating. And guess what? This is something we're interested in. So what is cooperation? It's basically paying the cost for one's person in order to convey a benefit to somebody else. But you might be wondering, well, Calina, isn't that against the Darwinian natural selection principle, which basically says that the strongest person survives? There is plenty of competition between individuals and between populations. And I would be saying, yes, you're right. But cooperation is known to be essential for populations to develop, both by basically common wisdom and empirical evidence. And it is the case from classes of cells to humans. If you think about it, humans start from being what, 2 cells, and then the cells proliferate and come to create organs, and then systems of organs, and then tiny humans, and then humans. And what those cells actually do, they cooperate together in order to develop such a complex system. So there you have it. So because it is so important, we want to find ways to promote cooperative behavior within selfish populations. And fear not, there's plenty of ways to do that. Direct reciprocity, A helps B. Indirect reciprocity, A helps B, B helps C. And what we're interested in today, institutional incentives, and in particular, we're interested in using reward and punishment in order to make people cooperate. Right. So we're interested in using institutional incentives in order to make people cooperate, but we're also interested in making it cost efficient. If you remember from the beginning, I said there's an external decision maker that's got the power to interfere in populations in order to achieve a desirable outcome. There's obviously a massive ethical concern here because, well, desirable according to whom and for whom, basically. This is not going to be discussed in the talk today, but I am planning on including it in my piece and perhaps talking to someone who's actually qualified to talk about stuff like that as opposed to popping in my own opinions. I could give you an example of positive interference, for example, and then a negative one. So in the case of a positive type of interference, think about improving maternal health care in order to up birth rate. And in the case of a negative type of institutional incentive, think about freezing a country's assets because one doesn't agree with the country's leaders, which obviously would lead to starvation and death. So institutional incentives don't always have necessarily a positive outcome. But for the talk at hand, this is a math talk. We're assuming everything's fine and the institution knows what it's doing. What we know is that this kind of institutional incentive enables large-scale cooperation. It is, however, costly, both in human resources and in equipment. So we're naturally interested in minimizing the cost whilst ensuring a sufficient level of cooperation. You might be wondering what sufficient means here, but again, this is maps, so we're just calling it a big letter, just as an example. If you're trying to pass a law in Parliament, that might be 51%. Don't quote me on that. I have no idea what the expression actually is. We're in the law building. If you're in a criminal court, we need beyond a reasonable doubt to send someone to prison. So again, it really, really depends on the context. What we know is that we want to minimize the cost while ensuring that level of cooperation. Right, so I've been babbling about ideas basically without actually diving into the maps. But here it is. This is a model. And in the model, we've got a well-mixed finite population of n self-regarding individuals that interact with their neighbors using a cooperation dilemma. A cooperation dilemma is basically a game in which, game theoretic-wise, one would be better off not cooperating, but for the good of the society, it would be great if the players would cooperate with each other. I.e., individual rationality leads to mass irrationality, is that a thing? Hopefully I've said that right. But basically, the first definition works really well. We've got a binary strategy. Individuals can either be cooperators or defectors. We are assuming a small mutation rate. And here mutation, well, it's kind of similar to its evolutionary definition. A defector, the chance of a defector popping out of the blue is quite small. The strategy update is based on the mutation dynamics, and is the probability here on the board. The probability of X copying Y depends on the fitness difference as well as the intensity of selection. And I want to walk you through what this means. So, if you've got a player X and he sees that player Y is doing better, naturally player X would be tempted to copy player Y. And we obviously see that throughout human history, like, I don't know, the Persian Empire adopting certain things that they've seen in the people they've conquered. And even nowadays, with my absolute favorite example, the YouTuber, Instagram, or TikTok, for example, everyone's adopted this kind of very modern job. Of course, they've seen that it brings lots of money. So, drawing back to the idea of survival of the fittest, obviously, if you see someone, well, doing better than you, you'd be tempted to copy what that person has done, hoping that would give you the same thing. Fitness here, usually in evolutionary terms, it's defined as the number of offsprings an individual has. This is game theory, so it's basically how a person playing the game, basically how large the payoff is. And something that's extremely, extremely important for our work is, again, beta, the intensity of selection, which shows how likely a player X is to copy another player Y. So, what I mean by that is the following. If the intensity of selection is low, no one is incentivized, can be incentivized to copy another person. There would be no point in using institutional incentives because no one would be drawn to copy somebody else. However, if the intensity of selection is a bit higher, then there would be a point using institutional incentives because people would be keen to copy somebody else who's doing better whilst playing the cooperation dilemmas. Right, this is all modeled on a Markov chain, and I was going to use the whiteboard pens to kind of show you what's happening. Sorry. These ones?
Yeah, well, black.
Okay.
Red.
Okay. Right. So we start at state 0, go to state 1, all the way to state n-1, and then state n. And there's obviously some rules to go to move from one state to another. State 0 basically means there's no cooperators. State n means there's n cooperators. 0 and n are absorbing states, so once you're in there, you can't get out. So basically, the ones we're interested in are states from state starting at state 1 to state Sn-1. I've written down on the board because it's really important for the investment policy. As you can see, it's theta k times the minimum. Theta k is the amount that the institution pays at state k. So say, I don't know, I can put it back. Say we've got sk here. The institution will pay theta k amount of money for the state sk. And obviously the entire amount would just be summing up of these states. Right, so the institution has given theta k amount of money in order to be used to reward and punish the people in the population. How do we decide if we're rewarding or punishing? Well, basically, we're timesing the amount by the minimum of the number of cooperators in the population divided by how strongly the cooperators feel the incentive, and the number of defectors in the population divided by how strongly the defectors feel the punishment. And that makes sense because if we've got a very high number of cooperators in the population, then there would be no point to further use the money to reward them. It would be better to punish the defectors, in order to slow them down. Equally, if we've got loads of defectors in the population, it would be better to reward people in order to encourage cooperation. As if the intensity of selection is above right, then other people will start copying the cooperators and we will achieve desired effect. To be fair, we've included A and B, which again show the efficiency of the reward and punishment respectively. But there's plenty of examples in real life where one will not be affected by an incentive. And that example would be if you've got a lot of money, you will not be affected by either reward or punishment. That's a talk for another day, perhaps a project for another day. But this is the investment policy we've used. Right, so the mathematical formulation is as follows. As I promised, the level of cooperation is denoted little omega, and it takes values between 0 and 1, just so we can easily translate them into percentages. What we want to do is minimize across all possible mixed cost functions that ensure that level of cooperation omega. That's the optimization problem, where theta 0 is that. The mixed cost function was obtained from the matrix of the Markov chain, which has got a very nice tree-diagonal profit shape. We're basically interested in what happens in these states because that's where a mutation can take place. And very, very important, the payoff, the difference in payoffs between cooperators at state K and defectors at state K is negative, but more important than that, it does not depend on the state K of the Markov chain. If it did, it would have made the math a bit more complicated. Right. I keep saying cooperation dilemma, and I have actually the ones that we've used. We've looked at the donation game and the public goods game. Again, just as a reminder, a cooperation dilemma is a game in which, although game players might be better off not cooperating, it's better for society if you did cooperate. The first one is a donation game. And you might have spotted that is just a generalized version of the prisoner's dilemma. If the players cooperate, they get a benefit at the cost of themselves. If they both defect, they get nothing. And if one of them defects and the other cooperates, the ones who defected gets the whole benefits without losing the cost, whilst the person that's cooperating will obviously loses the cost. In the case of the public goods game, we've got some players, here 4, sorry about the dollars, I could not find pieces with pounds. We've got 4 players and they've got the choice to secretly is very important because people behave differently when other people see them playing a game. So they can secretly put some money into a pot. The first 3 players contributed $20, whilst the last player contributed nothing. Once the money is in the common pot, it gets multiplied by a factor, here 1.2, and the amount gets redistributed equally among the 4 players. So as you can see, those that have contributed stuff got less money, whilst the person that's contributed nothing gets the highest amount of money. So again, game theory-wise, well done, he's won the game. But there are certain situations in life, I don't know, like climate change policies, in which it's better if players cooperate at a cost to themselves. Right, onto the maths, onto the fun part. Well, I hope everything else was fun, but going on to the maths. I've popped this big number there because it kept popping up throughout the analysis. So I wanted you to see what it is, what it's gonna make an appearance in the next slides. It's banded, it's convergent, it's great. We've seen it throughout the analysis quite a lot last year. So once that's out of the way, let me present to you the first result. And it's basically this one. It is always more cost efficient to use mixed incentives than to use either reward or punishment. However, if it's too costly for the institution to use punishment, then it's better if the mixed incentive turns into reward. And equally, if it's better to use punishment, then if it's cheaper to use punishment, then the external institution should do that. Right, this is also a numerical analysis seminar, so we brought in the numerics. On the figure here, we compared the cost for mixed incentives in blue, only reward in orange, and only punishment in green as a function of theta for a very small population, n equal 3, and 3 in beta. For the donation game, it looks the same for the public goods game. I don't know how much space on the slide. For the donation game with the benefit of 2 and cos 1. As you can see clearly from the pictures, mixed incentives are the cheapest option. And again, the analysis has confirmed that. Next, we've further analyzed the cost function, and we obtained the weak and strong selection limits. As a reminder, the intensity of selection is just how likely a player is to copy another player. Well, basically that's the weak selection limit. And the second one is the strong selection limit, and it depends on the difference between the payoff of cooperated and the payoff of defectors. I've got a pretty picture to follow. Right, just to let you know, on the left-hand side, we've got a donation game with benefit 2 and cost 1. And on the right-hand side, we've got the public goods game with C is basically how much they're contributing, R is the multiplying factor, and N is the number of people in a business group. The red dashed line is the weak selection limit, and the green dashed line is the strong selection limit. And as you can see, our cost function Emax, which is the blue one, stays between the 2 limits with varied beta on the graph. We've also looked at what happens when the population number tends to infinity. And we've got these 2 limits for the donation game. Obviously, they both depend on the intensity of selection and the cost in the case of the donation game. and the intensity of selection, the cost, the multiplying factor, and the number of people in a group for the public goods game. Left-hand side, we've got the donation game with the same parameters. Right-hand side, we've got the public goods game. We've varied n in the graph, and we can see that the mixed cost function in blue follows the limit, which is a dashed orange line. We've also bounded the cost function between two values, which depend on theta, which is that theta there, how much money the institution has used in total, the number of people in the population n, H and AB, and how efficient the reward and punishment are. Right, this picture here is going to be very important for what's coming next. I firstly wanted to show you that our cost function exhibits a phase transition, and I will explain to you, hopefully, well, how to get the values, how to minimize the cost, because this is what we're trying to do, minimize the cost while ensuring a specific level of cooperation. In this example, we selected 70%. Right, so we've got the behavior under the threshold and the behavior above the threshold value. In the case of the behavior under the threshold value, we calculate an optimal beta called beta star. When the beta in the game, which is simply called beta, is less than or equal to beta star, the function is non-decreasing, as you can see here. And when it's greater than beta star, when beta is greater than beta star, it's increasing, then it's decreasing, and then it's increasing again, so it's not monotone. In the first case, when beta is less or equal to beta star, our minimization problem can be solved by plugging in theta 0, which I put on the slide here, and is dependent on the number of people in the population, the strength of selection, and the level of cooperation, as well as the difference in payoffs between cooperators and defectors. And in the case here, the dashed red line is basically theta star, which is the same as theta 0. So theta 0 would be minimizing the cost function, and our problem would be done. In the case of above the threshold value, so when beta is greater than beta star, we've got two other values, theta 1 and theta 2, for which basically I'll show on the picture. The function is decreasing here and increasing again. This is theta 0, and we're trying to figure out if either theta 0 or theta 2 would be, theta 2, which is defined like that, would be minimizing the cost function. So our problem turns into this one at the bottom here. We are plugging in theta 0 in the function and then theta 2, and we're interested in obtaining the minimum. In both cases, we are solving the problem. Well, the beta less than or equal to beta star is shorter. Beta greater than beta star is a bit longer, but we're still happy. We minimize the cost whilst ensuring a sufficient level of cooperation. I've got all the numerical simulations as well if people are actually interested in seeing how we've done this. F is a polynomial, which is, well, obtained from other polynomials, and basically, beta star is a root of this polynomial, as you can see here. When we are above the threshold value, we need to check those two values, theta 0 and theta 2, to see which one minimizes the cost. And when we are below, we use theta 0 to minimize the cost of the cost function. Right. So I've presented to you a cost-efficient interference mechanism for promoting cooperation. People have looked at reward or punishment, well, separately, and they've even looked at reward and punishment together, so hybrid incentives, but they haven't actually haven't taken into account minimizing the cost whilst ensuring a sufficient level of cooperation, which is one of the new things we've got to the game. We've done a rigorous analysis of the cost efficiency function, and we've obtained asymptotic limits, the weak and strong selection limits, and the infinite population limits, as well as have improved phase transition. You might be wondering what's next. There are a few further research paths that one could embark on. In the beginning, I did mention that we've assumed a small mutation rate, so it'd be great to see what happens at any mutation rate. Spoiler alert, probably the math would be harder. Also, looking at a more complex game in which the state of the market, the difference in payoff between corporates and effectors would depend on the state of the Markov chain would be really nice to look at. Again, spoilers, that would mess up with the nice two-diagonal chocolate shape, which allowed us to calculate the cost function in the first place, which we could probably tell the problem from translation, but that remains to be seen. I'm sure that even looking at the numerics would be really interesting if that happens. In our population, everyone's interacting with everyone, which clearly doesn't really reflect their life. I'm sure you haven't either. So copying the players on the graph and making them interact with their neighbors would be very, very interesting. It might be a work factor, but not that I'm not doing. It would most certainly be a bit more to do. And last but not least, I haven't included on the slide just so you don't steal my ideas. I'm joking, I'm sure we'll do that. What we're looking at at the moment is in the previous game, the one that I've been talking about for the last half hour, the external institution punished and rewarded everyone in the population. So what happens if the external institution, the decision maker, would be punishing or rewarding only T of those people, or would be punishing and rewarding both the first T and the last T? If we were to rank the people that cooperate and the people that don't cooperate and punish just a fraction T of those and reward just a fraction T of those. Well, we're hoping that will be more cost efficient. I can't do anything now. We haven't really got much into that, but it would be really, really interesting to see if that would actually bring an improvement in the cost efficiency. Right. That's it for me. Do you guys have any questions?
Yes.